Hello, everyone. So today we're going to begin our discussion of lab hazards and the importance of identifying what hazards may be present in the lab and walking over a couple of major hazard categories. So we're going to start off this section on a little bit of a dark note by talking about the radium girls, who's a classic example of why it's important to know what hazards are present in your lab. The label Radium Girls essentially talks about a series of several hundred employees of the American Radium Corporation, who essentially paid young women to paint radium luminescent paint, so glow in the dark paint, onto watch dials. And so this paint included radium, and to make sure that their painting was precise, they were asked to lick their brushes every time in between dials in order to maintain a fine tip. It turns out that none of them were informed that radium was in fact very unhealthy and could cause long-lasting conditions. Many of them suffered from what was called radium jaw, at which point they had radium embedded in their jaws that was slowly dissolving the bone. So, most of this happened because nobody was informed of what the dangers of radium itself was. So, before you work in lab, I highly encourage you to know exactly what materials you're working with and what dangers they may pose. Because it turns out sometimes they aren't so nice. And if you want to know more about the Radium Girls, I highly encourage you to pick up the book. It is quite a story of how chemistry can go wrong. So today we're going to start with a quick overview of the major types of hazards that you may encounter in a typical chemistry lab. So we can divide these into several major categories, the first of which is a physical hazard. So these are things that involve actual physical dangers. So these are the ones that we're typically used to thinking about in other sort of environments. We also have to watch out for mechanical dangers. So these are anything that involves machinery or moving parts, which may be a lot more common in a chemistry lab, and especially in a lot of biology labs than you think, and they can sneak up on you sometimes. And then we have the rare but important radiation hazards. And here's for all of you biochemists out there, make sure you're aware of your biological hazards and chemical hazards, which is going to be the focus of most of this unit. So we're going to go ahead and start by focusing in on these three first categories, physical and mechanical, which you're probably mostly aware of, and radiation, which we encounter a little bit less frequently. And in subsequent lectures, we're going to talk about biological and chemical hazards. Though it's worth noting that a lot of hazards belong to multiple categories. For example, you may have a highly pressurized gas cylinder, which has a lot of physical hazards due to being a highly pressurized gas. But it may also have chemical hazards if it tends to be some sort of toxic gas like hydrogen sulfide. So again, just because something belongs to one of these categories doesn't mean that it doesn't belong to one or even all of the other categories. So make sure that you're very aware of what hazards you might be dealing with. So let's go ahead and talk with about the classic physical and mechanical hazards. So the first one isn't exactly a direct hazard, but it's the classic fire hazard, which is pretty much anything that inhibits movement. So you're often going to hear a lot of your instructors and hopefully your fellow lab mates talk to you about things that essentially block hallways or inhibit the ability of you to move smoothly around a lab. And so if you ever have me in lab, you'll notice that one of my pet peeves is the open drawer. Simply because an open drawer is essentially a recipe for disaster, as it's easy for someone to bump their knees against it which again can just be bruising, but becomes quite hazardous if the person who hits their knees or legs against the drawer happens to have, say, a flask of 6 molar sulfuric acid. So again, watch out for fire hazards. We also have typical dangers like wet surfaces, which can uh, cause slipping or sliding of chemicals. I have seen more than one flask broken because it was put on a wet surface and slid. But also watch out when wet surfaces combine with electrical hazards. So try and keep any wet surfaces away from, say, frayed wires. But it's also very easy for a chemical lab to have an overloaded socket if you're trying to use a little bit too much machinery. Also, as I've brought up previously, watch out for sharps. So this is the classic needles, which are often used with a lot of gas work, as you may need a needle to puncture a septum or to deliver a gas sample. But it also includes the ever classic broken glass. And this may not just be big chunks of broken glass from, say, flasks, but it can also be smaller chunks of broken glass that may come from something as insidious as a pipette tip, as those are much harder to see and can still stick in your finger. Then we have our classic issue of hot surfaces, because as you'll hear every chemical instructor say, hot glass looks the same as cold glass, and a hot plate looks the same as a cold one. And I have had more than my fair share of students with burned hands. But we also have the more obvious issues like open flames, which can be become really dangerous when combined with chemical hazards such as flammable materials. And on the other side of hot surfaces, we also have cold and cryogenic surfaces, as which can become quite dangerous when you start working with specific cold chemicals like liquid nitrogen, which we'll talk a little bit more about later. But we also have things like overpressurized lines. So this can include overpressurized gas samples, such as cylinders, which most people tend to think about. But it also can include overpressurized liquid lines. A famous example was in a physics lab at the University of Minnesota, where they had a newly renovated building where they installed nice new water lines. Well, you know how you have the spigots on the water lines inside your hoods? Well, it turns out that one of them had been overpressurized and promptly set a spigot shooting 50 feet across the room and left a dent in the opposite wall. So just because something is built in doesn't mean that it can't be dangerous. So watch out if you notice that any line in your lab, liquid or gas, might be holding a little too high of pressure. Then we have our classic explosion hazards, which can quickly get into chemical. And a lot of people forget about this one, but it turns out that a lot of equipment in a lab can be quite noisy. So if you think that something is a little too noisy, try and get in a noise meter. If the sound is sustained at over 85 decibels, this is considered an official noise hazard. And if it only goes for short bursts, but it's over 100 decibels, again, this is considered a noise hazard. OSHA will shut us down if we have these, so please let us know if you find something that's too loud. And then, especially as we work into mechanical hazards, watch out for anything that can be crushing. So this can be anything from just a heavy cylinder to moving parts such as centrifuges, because centrifuges can also present a crushing hazard, as well as things such as a centrifuge operating at high speeds with a volatile sample can also lead to things like overpressurization. So again, just because a situation has one type of hazard doesn't mean that that other hazards won't be present. And then again, also make sure that you watch out for improper ventilation, especially depending on what chemical systems you're working with, and temperature control, as we'll talk about much later when we're talking about chemical hazards. That one way to prevent dangers is keeping your conditions under the right temperature regime, which often means a little colder than we'd like. So these are the classic physical and mechanical dangers that you're probably mostly aware of from everyday life. But typically you don't work with radiation. And it's worth noting, while radiation tends to have one of the worst reputations, it tends to in general be one of the least dangerous, simply because we're less likely to encounter a radioactive sample, and simply because once you know you have radiation, it can be very easy to manage. So we can divide our radiation into three major categories, the first of which is called non-ionizing radiation. So this typically consists of low energy electromagnetic radiation. So this is any essentially electromagnetic field where the photon contains energy less somewhere between 10 to 30 electron volts. We'll talk a little bit more about this later, but this essentially translates into any wavelength of light longer than about 300 nanometers. So this includes visible, IR, radio wave, and microwave. We also have ionizing radiation. This is the one that a lot of people tend to think about. This is going to be your X-rays and gamma rays, and can be thought of as any wavelength pretty much lower than 300 nanometers. And it turns out that this one actually can be really hard to stop and can be quite dangerous. And then we also have particle radiation. So this essentially is a catch-all term for highly charged energetic particles that are bigger than a photon. So let's go ahead and start with this idea of non-ionizing radiation. So if it's non-ionizing, this means it's low energy. So our biggest worry about non-ionizing radiation is only going to really happen if we have high intensity sources. So this can include things like UVA, which can in high intensity do skin damage, because think about sunlight. But it also includes things like visible light and IR. So visible light, you're mostly going to have to watch out about eye damage, and infrared can be interpreted as heat, so it can start racking up the skin damage. But it also includes things like microwaves and radio waves. So these are typically only dangerous at very high doses, and this will likely only have potential consequences, mostly in terms of heating. And then we've got very low frequency electromagnetic sources, which essentially can be translated as magnetic fields. So these generally are going to be very safe for anything living. So if you've got biological tissues such as you, they're just fine. But watch out, because if you start getting to very high intensity, very low energy electromagnetic fields, this starts translating into things like your NMR, which can be a little bit more dangerous for metallic or electronic objects. So watch out if you've got a pacemaker or any piercings, or it may, you're very likely, if you spend a lot of time around NMRs, to at least to murder at least one credit card. So non-ionizing, generally fairly safe. This brings us to our ionizing radiation. So we've now worked our way through radio wave, microwave, IR, visible, ultraviolet. Now we're talking about X-ray and gamma ray. So these ones are the ones that can start causing tissue damage and carcinogenic behavior. So even when you start working into the far UV, this is the point where you start having a lot of the cancer-causing effects of sunlight, such as the classic example being UVB radiation. The two major types of ionizing radiation we really have to worry about are X-rays and gamma rays. So These are mostly going to be emitted by equipment. So, and occasionally the very rare short-lived isotope. But again, most of the time you're going to have to watch out for X-rays or gamma rays is when working with high energy spectroscopic methods. So usually you're going to know very much when X-rays or gamma rays are present. They tend to be directional, and you're almost always going to be provided with protective equipment. And this leads essentially to one last major category of radiation, and this is the ionizing particle radiation. So this is the one that you may have heard us talk about at the end of general chemistry. So this is the idea that certain atoms can decompose and release certain types of particles. So hopefully you're familiar with the idea of alpha radiation, which can be thought of as pretty much a helium nucleus. So 2 protons, 2 neutrons, no electrons. So this one can actually doesn't typically travel that far, typically about 3 centimeters in air or about 0.04 millimeters in biological tissue. And the reason it doesn't travel that far is it's pretty much going to either, if it has enough high enough energy, combine with another nuclei, or simply steal 2 electrons and become fairly safe helium. So it turns out that you can block block alpha radiation with a sheet of paper. However, when alpha radiation becomes truly dangerous is if you ingest the alpha emitter. So this is what made radium so dangerous. Radium tends to be mostly an alpha emitter. So if you've got an external source of alpha radiation like radium, you're usually fairly safe. So I'm fairly safe to have a radium watch dial. Where you have to watch out for is ingestion, because it turns out that radium can actually take the place of calcium in your bones, at which point you now have an alpha emitter inside your bones, which can promptly do a really good job at providing toxic radiation to everything within about 0.4 millimeters of your bones. And so while an alpha emitter outside you really won't penetrate your skin, an alpha emitter inside of you is one of the more frightening prospects. So if you are working with alpha radiating materials, especially ones that emit a fair bit of alpha radiation, be very cautious about ingesting anything. The other major type of ionizing particle radiation is going to be beta radiation. So this is essentially a high energy electron. This one can actually travel a fair bit further in air, so about 16 centimeters. But again, will barely penetrate your skin, so not getting much more than a half a centimeter through tissue. So beta radiation, you typically actually need to have some sort of minor shield, but things like cloth will typically block a lot of radiation. So again, unlike gamma radiation or X-ray radiation, you often don't need your lead vest or specialized clothes. Typical attire, though maybe more complete than you're used to, will stop both of these. However, again, one of the things you have to be very aware of is whatever your particle source is. What's the half-life? The longer the half-life, the lower dose of radiation you're likely to receive, but the more insidious it might be over a long-term side effect. So if you're working with a lot of particle radiation, a lot of materials that can emit particle radiation, one of the biggest things you're going to want to do is make sure that you just minimize your exposure. So try and use the smallest amount that you need and try and use the safest isotope. An alpha emitter over a beta emitter over a gamma emitter typically. And again, make sure you use the appropriate type of shielding. So a lighter shielding tends to work for alpha radiation, but you'll need lead shielding if you're working with X-ray or gamma. But the biggest thing is, especially when working with radioactive isotopes, please make sure you minimize internal exposure. So this means if you even think you are near a radioactive material, no eating, no drinking, no chewing gum, no touching your eyes or mouth, nothing that can possibly move the particles from outside you to inside you. That's where essentially the worst side effects start coming. And again, proper labware is always important. And one of the more unique things to radiation safety is an emphasis on disposable labware in case the radioactive particles embed in your clothing. Because while I might not have to worry about something with that can only travel, say, half a centimeter, that can be problematic if it is in my clothing. So if you're working with radiation, your workplace should you should be aware that your workplace is making several accommodations. First, they should try and monitor the radioactive levels in the air moving around the system. Monitoring personal exposures, such as things as radiation badges, are often very important. And watch out for things like bioaccumulation. So even if everything around you may not have a high degree of radiation, if you're ingesting enough material over a long enough time, it can accumulate in your body. So sometimes tissue samples of any workers working intensely with radioactive materials are very useful. And hopefully your facility is going to make use of several key features. First of all, make sure that if a room contains radioactive materials, it has the appropriate warning signs. Again, inventory control, so that you know where all the radioactive material is at all times, so it doesn't end up someplace it shouldn't be, which is again part of good housekeeping. But good housekeeping also includes things like regularly cleaning your lab to prevent an unintentional digestion. And again, probably one of the things that's the most important with radiation safety is proper waste disposal, as a lot of radioactive materials, because it can bioaccumulate, is a little bit more important to pay attention to exactly what happens with your waste than other materials. Though depending on the half-life, less intensive procedures may be needed. So again, make sure that whenever you work with a radioactive material, you know what the proper technique for waste disposal is. So next time, we'll continue talking about hazards as we get outside of my comfort zone and where a lot of you care with biological hazards. Till then, take care.